Lesson 38, graphing logarithmic functions, finding inverses of logs and exponential functions, and solving using natural logs. I would pause this, next slide, and I would write down what you see. The graph on the left is representing an exponential parent function. I'm using the table of values of 0, 1, 2, 1b, b squared. My horizontal asymptote is y equals 0, domain all real numbers, and the range is going to be y is greater than 0. My logarithmic function, which is an inverse of exponential, everything flips. The x's become y's, the y's become x's, so my new table is going to be, for x values, it's going to be 1 base squared, and for y values, 0, 1, and 2. Vertical asymptote x equals 0 for the parent function. My domain x is greater than 0, and my range is all real numbers. Let's get to practice. So if we had to graph f of x was log base 2 of x, the first thing I'd ask you is the log isolated? And what I mean by that is if I look for an a value or a b value or an h value or a k value, are there any that exist that I could maybe get rid of in terms of a's and k's? The answer to this question for this example is no. The log is isolated. There are no h's and k's, so we can then convert to exponential. In a few examples, we'll have a k, so we'll get rid of it, and I'll show you how. To convert to exponential, we're going to use the property that when we have a log, we're given a base, so our base is going to be 2. We're raising it to the power of f of x, and then we're going to equal that to our argument x. Then I'm going to make a table of values. Remember, I gave you a table of values on the first slide, so we know that it's going to be y's are 0, 1, and 2. Then I'm going to plug in f of x because notice f of x is now my independent once I've converted it to exponential. So if I plug in 0, I'd get 2 to the power of 0, which is 1. If I plug in 1, I'm going to get 2 to the power of 1, which is 2. And if I plug in 2 for the y, I'm going to get 2 to the power of 2, which is 4. To find your domain, you're going to take your argument and set it greater than 0. In this case, x is greater than 0, so my domain is 0 to infinity. My asymptote is going to be x equals 0, and my range, well, all logarithmic functions have a range of all real numbers. Now we're going to graph what we see. Well, we see that the domain's happening at x is equal to, x is greater than 0, and our asymptote is x equals 0. We're going to graph what we have on our table. Remember, on our table, we're just graphing the x's and y's that we see. So we're going to graph at x is 1, y is 0. We're going to graph at x is 2, y is 1. We're going to graph at x is 4, y is 2. You're going to put some arrows on both sides, and you're done. Next example. Graph f of x, which is log base 2 of x plus 4. Again, the first question you want to ask is your log isolated? Is there an a value? No, it's 1. And is there a k value? No, it's 0. So then you can convert it to exponential. We're going to take the base, which is 2, raise it to the power f of x, and we're going to equal that to x plus 4, our argument. Now in this case, I want to get x alone so that once I have some numbers on my table, I'm going to just get x values to write down on the table. So to get rid of that 4, I'm going to subtract 4 on both sides. So I get 2 raised to the power of f of x minus 4 equals x. I'm then going to make x's and y's. Again, y's are going to be 0, 1, 2 for now. And then we're going to plug in. So plug in 0 for your f of x. So you're going to get 2 to the 0, which is 1. 1 minus 4, negative 3. You're going to do the same with 1. 2 to the 1 is 2, minus 4, negative 2. 2 to the power of 2 is 4. 4 minus 4, 0. Then we're going to find our domain. Remember, you take the argument, in this case, x plus 4, set it greater than 0, solve for x. I'm going to get something like x is greater than negative 4. So I'm going to get x is greater than negative 4, converts to negative 4 to infinity. Your range for any log is all real numbers, and your asymptote is the domain value of x equals -4. Remember, it's an equals, not an inequality. From here, we're going to graph what we see. We see that x is going to be -4. So we get x equals -4. That's on our graph now. And then we graph what we have on our table. When x is -3, y is 0. When x is -2, y is 1. When x is 0, y is 2. Put some arrows, and we're done. Next, you're going to graph f of x is equal to log base 2 of x plus 4. How this is a little different than the last one is that this one is missing parentheses on our argument. So this is the log that I need to isolate. Is that log isolated? The answer is no, because I see this plus 4 on the outside. So to convert it to exponential, first I need to say, well, that means it's f of x minus 4 equals log base 2 of x. Now I'm going to consider, is that log isolated? Yes, it is. So I'm going to do base, which is 2, raised to the power f of x minus 4 equals x. Now, I like that it equals x. I don't have to manipulate anything. The problem is that if I were to plug in 0, 1, and 2, if I plug in 0 for f of x, right, because that's what I have on my function. If I plug in 0 for f of x, I'm going to get 2 to the -4. Well, 2 to the -4 is equal to 1/16. Now, that's kind of hard to graph. So what I would suggest you do is think what number for f of x would make the exponent be 0. And in that case, you would put 4. 4 minus 4 is 0, so 2 to the 0 is 1. Then you go up by 1 on your y's, so plug in 5. So 2 to the power of 5 minus 4 is 2 to the power of 1, which is 2. 2 to the power of 6 minus 4, well, 6 minus 4 is 2, so 2 squared is 4. Now again, we're going to find the domain. In this case, the argument of the log is x, so x is greater than 0. That's going to be 0 to infinity. Your range for any log is all real numbers. Your asymptote is the domain value with x equals symbol. And from here, graph what you see. I see that I have an asymptote at x is equal to 0, so I'm going to label that x equals 0. I'm going to graph whole number values because like 1/16 is kind of really hard to graph. So I'm going to start at x is 1, and I'm going to go to y is 4, x is 2, y is 5, x is 3, nothing because I don't have that, but x is 4, y is 6. From there, put some arrows indicating your negative infinity for the range to infinity, and you're done. I'm going to change it up a little bit, and we're going to graph a natural log. So imagine I gave you a graph natural log of x minus 2 equal g of x. Step 1, again, is the log isolated? So when I look at the log, is there anything outside of it, in the front of it and behind it? In this case, no. So we're going to convert it to exponential. What is the base of a natural log? That would be e. What is the power I'm raising it to? G of x. What's it going to equal? X minus 2. From here, again, you always want it to say x equals because then it goes right on the table. So we're going to go e to the g of x power plus 2 equals x. Things we might need to know before we start this. We need to know that e is approximately 2.71. We need to know that e squared is approximately 7.38. Then when we set up our table, notice your exponent. Does your exponent have anything other than just g of x? If it does, you might want to alter the table. Since ours does not, I'm going to say 0, 1, and 2 is my friend. From here, I plug in 0. E to the 0 is 1. 1 plus 2 is 3. Plug in 1. E to the 1 is 2.71 approximately, and if I add 2 to that, I'm at 4.71. If I do e to the squared value, that's 7.38, and if I add 2, I'm at 9.38. From here, I look at my domain. So to find the domain, again, we're going to take the argument, which in this case, x minus 2 greater than 0, so x is greater than 2. So we can say that we're domaining from positive 2 to infinity. Our range, just like any other log, is all real numbers. From here, my graph doesn't look very set up correctly on the line, so I'm going to fix that. And then your asymptote, again, take the domain value x is equal to 2 every time. So I'm going to set up my graph. I'm going to make it really high in the x positive area because, well, I know that I'm going to go in high numbers for x's. So when I set up my asymptote is going to be x is equal to 2. So I'm going to graph x equals 2. There we go. There's x equals 2. I'm then going to graph what I see. 3, 0, 4.711. Now, I don't know 4.71 just other than it's over 4 and less than 5. So there we go, 4.71. Then I have 9.38. And then 2. So 9.38, 2. Something like that. You're going to put some arrows and connect them. Done. Next, we're going to move into the second part of the lesson. This is when you're going to be asked to find the inverse of the following and then state the domain and range. I'm going to state the domain and range of both the function and the inverse since it doesn't clarify. So if I looked at this function, I have the log function. So I can find the domain of this function by setting the argument greater than 0. And that's going to be x is greater than -5. So I can write the domain as -5 to infinity. Again, that's the domain of the function. The range of the function, well, for all log functions, I have all real numbers as my range. To find an inverse, I'm going to do a few ideas. Step 1, I'm going to ask myself, is the log isolated or is the exponential isolated? In this case, yes, the log is isolated, so we can move on to step 2. I'm going to switch my f of x with x, and I'm going to switch my x with y, because inverses switch x's and y's. From here, I'm going to convert this statement to exponential. So I'd have 3 to the power of x is equal to y plus 5. And from there, I'm going to isolate the new y, and I get 3 to the power of x minus 5 equals y. Last thing I want to do is write this in function inverse notation. So 3 to the power of x minus 5 equals the inverse function. To find the domain of the inverse function, I look at the previous's range. The previous range is y values, so it's going to be the domain of my inverse function. When I look for the range of the inverse function, I'm going to literally look at the previous domain for my function, and that's going to be the range of my inverse function. And you'd be done. Things you need to remember is that the range of this is going to be y is greater than -5 because range is always y values. And you're good. That's a statement. Next example. Find the inverse of the following, state the domain and range. I'm going to do the domain and range of both again. Here I go. So the domain of this guy. Well, I'm dealing with exponential functions, and if I remember real quickly, an exponential function looks like that. So the domain of it is going to be all real numbers. The range is where students get a little tricked, so I'm just going to pause on the range, and I'm going to use my logarithm to help me with that. From here, I'm going to look and say, is the function isolated? If it was logarithmic, I would just want to log. This is an exponential, so I'm going to want to say, is that e to the power of x isolated? The answer to that is no. So I'm going to move the 2. So g of x plus 2 equals e to the power of x. Now from here, the e to the x is isolated. So now I'm going to convert this from exponential to logarithmic form. I got to remember to do that, I'm going to do log to the base of what I'm seeing, which is e, with, oops, just kidding. Don't I have to convert this into an actual inverse by switching the x and y. So I want to call that x plus 2 equals e to the y power. From here, I can then say, now I'm going to convert it to logs. So again, log, the base of this function is e. I'm going to use an argument of x plus 2, and I'm going to equal that to y. My last step of writing a function as an inverse is make sure to write the y, the new y, as the inverse function. So inverse function is equal to, and then things I got to remember is that log base e is known as the natural log of x plus 2. So if I think about this guy, when I find its domain and range, so I'll put this in purple, the domain of this log, I'm going to do x plus 2 is greater than 0, so x is greater than negative 2, which means I have negative 2 to infinity. My range for the inverse, again, all real numbers. Notice what I was saying. The domain of the first one becomes the range of the inverse, and then the domain of the inverse becomes the range of the original function. So things I could know now is that my range was probably negative 2 to infinity. Why is that? Because we're dealing with inverses. Next, we're going to move into what's called solve by using natural logs. So if I wanted to solve this using natural logs, that means that I have to use natural log instead of a log base of what I see. So I see a 3 in this problem. So I could use log base 3, but the questions want us to use natural logs. Makes it a little more tedious, but I will say when you get to calculus, it is going to help you with your skills. So let's try it. First, I need to isolate my exponential. So I'm trying to isolate this. So I would need to first get rid of the 14 by minusing it to both sides. So negative 3 to the x minus 3 equals negative 12. From there, divide both sides by negatives. So 3 to the x minus 3 is equal to 12. Now from here, we're going to use a property that we learned in the last lesson that said if I had the natural log of x equals the natural log of y, I could claim the arguments were equal. I'm going to now do what the opposite of that is. I'm going to go backwards with that skill. I'm going to say, well, if I know the arguments are equal, then I'm going to natural log both sides. So I'm going to call this the natural log of 3 raised to the x minus 3 is equal to the natural log of 12. From this part, I can take the x minus 3 and use the property of if I have an exponent, it can become a coefficient of a log. So I have x minus 3 times the natural log of 3 equals the natural log of 12. From here, this is where students get a little stuck, and they divide both sides by natural log of 3. You could do that, but if the question said write it as one single log, it makes it a little more difficult. So I would suggest taking this number, which is the natural log of 3, and distributing it to each term. So you get x natural log 3 minus 3 natural log 3 equals the natural log of 12. From this statement, I need to again get x by itself. The problem is solved, so I'm looking for x. So now I have to move this statement of 3 natural log 3. Well, to do that, you can just add it to both sides. So x natural log 3 is equal to the natural log of 12 plus 3 natural log of 3. From here, I'm going to use log properties on the right-hand side. I'm going to use 2 of them. One of the properties says if I have an exponent or coefficient, I can make it an exponent. The other property says if I have 2 logs adding together, I can multiply the arguments. So I'm going to simplify the right side and call the left side x natural log of 3 equals the natural log of 12 times 27. From there, to get x by itself, I have to understand that x is multiplying the natural log, so I can divide both sides by natural log of 3. So I'm going to get x is equal to the natural log of 12 times 27 divided by the natural log of 3. Some students think that you can actually divide the 12 and the 3. The answer to that is you cannot. So this would be my final answer. You could multiply 12 times 27, but I'm not going to. Next problem. This next problem says I have 50 divided by e to the 2x minus 14, and I'm equaling that to 25. I'm going to go off to the side and give a fraction rule that I should know. It's okay if you don't. I would just make sure I know this. If I had something like x divided by m is equal to some n, this equivalent statement can be written x over n equals m. To do that work real fast, I multiplied both sides by m and canceled the m's, and then I divided both sides by n to get what I have at the last statement. If you need to show that work, maybe do that off to the side. I'm going to use this property, however, to now simplify my question that I've been posed with. I see that I have 50 as a numerator and 25 as the equals number. So I'm going to rewrite that and say that I actually have 50 divided by 25 is equal to e to the 2x minus 14. Again, I'm using the property up on the fraction side on the right. From here, I can claim that that's 2 equals e to the 2x minus 14. 14 is not an exponent, just to be clear. I need to go back and fix that. I wrote that in my problem. Not good. So 14 is not an exponent, so make sure it's not an exponent. From here, I'm now going to say, well, to move the 14 to the other side and isolate the e so I can convert to exponential, I need to add both sides to 14 on both sides. So 16 is equal to e to the 2x. From here, you have some options. You could 1/2 both sides to get rid of the 2, or you could natural log both sides here, and you would still end up with the same answer at the end. So again, you could 1/2 both sides. I'm going to do that because it's going to get rid of my exponent of 2. So I'm going to get 4 is equal to e to the x. From here, I'm then going to see that if I have base power equals argument, I can convert that to a log, which is called the natural log of 4 equals x. And that would be my solution. On to the next. You're going to get something like this where you get x's on both exponents of an equation. If you get this, this is like that property where if I had the natural log of x equals the natural log of y, we claimed that x was equal to y. So I'm working this property again backwards. I know the bottom to be true, so I'm going to natural log both sides. The natural log of 2 to the power of x plus 4 is equal to the natural log of 6 to the power of x. From here, my exponents are allowed to become coefficients, so I would get something like x plus 4, the natural log of 2 equals x natural log of 6. From here, I'm going to get something like x natural log of 2 plus 4 natural log of 2 equals x natural log of 6. Again, I did this wonderful thing called distribution, which we learned in Algebra 1. Don't be lost. I got you. Now from here, this is where you may be like, I'm solving for x, but I see 2 x's. So what I'm going to do is take the one I see on the left-hand side, and I'm going to move it to the right. I'm going to keep my argument bigger as the first statement. I'm going to make the negative one the smaller argument. So I'm going to call this statement the natural log of 2 to the 4th power, because I'm making that a number so I can get rid of the coefficient, equals x natural log of 6 minus x natural log of 2. From this point, I'm going to notice they both have an x in common. So I can now factor x away. So this is where factoring comes into play. So I have the natural log of 16 equals x times the natural log of 6 minus the natural log of 2. From there, I can use a log property that says if I have minus between two logs, I can make the arguments divide. So the natural log of 16 is equal to x natural log of 6 over 2. 6 over 2 can be reduced to 3. So I have the natural log of 16 equals x natural log of 3. And then I can convert that to the natural log of 16 divided by the natural log of 3 equals x. That's solved using natural logs. Done. Last but not least, you could get a question like this, where you have e to the 2x equals 3e to the x plus 10. If I had to solve using natural logs, things I might think about is this kind of looks like a quadratic. X squared equals 3x plus 10. I kind of see that. So what I'm going to do is I'm going to say let u equal e to the power of x. If I let u equal e to the power of x, then I'm going to get something like u squared equals 3u plus 10. From here, I have a quadratic that I need to set equal to 0. So I'm going to move the 3 at u, move the 10, so I get something like u squared minus 3u minus 10 equals 0. From there, I'm going to see if I can factor. What multiplies to negative 10 that adds to negative 3? Well, that's going to be u minus 5 times u plus 2. From there, I'm going to go back to the original statement, e to the power of x. So e to the power of x minus 5 times e to the power of x plus 2 is equal to 0. So now I can use the zero product property that says if I have two statements multiplying to equal 0, I can set each factor equal to 0 and solve. So e to the x minus 5 equals 0. E to the x plus 2 equals 0. That would give me e to the x equals 5. E to the x equals negative 2. From here, I have exponential, so I need to convert to log. The natural log of e to the x is equal to the natural log of 5. The natural log of e to the x is equal to the natural log of negative 2. There should be something screaming in your head saying when you have natural logs or any logs, the argument's never allowed to be negative. There should also be another property screaming in your head that if you have the natural log of e to the x, you really just have x. That means my final answer for this would be x is equal to the natural log of 5, or x is equal to the natural log of negative 2. And again, screaming in your head would be that the argument is never allowed to be negative. So your final answer for this one would be the natural log of 5. That's it. Have a great day.